Alright, so extra practice problem 6.10. This is probably the most complex problem we've seen all module. So we have a man pulling two boxes across the floor with a force 1750 newtons. Taking friction into account, what is the acceleration of the boxes and the tension in the rope between them? So we haven't taken friction into account when we have two objects with a rope. So this is a bit more complex than some of the other stuff we've seen. So let's make a diagram. We always start with the rear object, just because it's a bit easier to assemble your equation. So we're going to look at the box in the back. And they give us the mass as 150 kilograms. And then what we're going to do is look at the forces that are acting on this box. So we have tension going this way, and then we have the weight of the box, and then the normal force, Fn, and then to the left, resisting the movement to the right, is friction. So this is what our little box will look like. All the forces. So 4 different forces right now. And so you may be thinking, how are we going to figure out acceleration from all of this? And this isn't much difficult than the other problems that we've done with two objects and a string between them. So first thing we're going to do is solve for the friction. So we have little f equals coefficient of kinetic friction times the normal force. You remember this from previous modules, you know? It's a simple equation. So we can expand that. They give us coefficient of kinetic friction as 0.35 times the normal force, which is the opposite of the weight. We're going to define upwards as positive and right as positive. So weight is negative and F is negative. So because of that, we'll have the weight, which is the 150 kilograms. We're going to multiply that by 9.8. And we're going to have two significant figures in our answer. It's going to round to 1500 newtons. So 0.35 times 1500 newtons. The frictional force is going to be 530 newtons. Okay, that wasn't too hard. So now we already have F going this way. Now we need to sum up these forces. And what we're going to have is, we're only going to be looking in the horizontal dimension, the F and the T, because up here, there's no movement. The box isn't going up, it's not going down. The box is going to the right. It's being pulled this way by the string. So, we're going to have sum of forces equals mass times acceleration. This is, basic equation. You gotta remember this. And in this case, the sum of the forces is tension, which is positive, plus friction, which is negative because it's going the opposite direction, equals the mass of the box, 150 kilograms, times acceleration. And we don't know what A is. That's what we're trying to find. So we can plug in the negative F, so T minus 530 newtons equals 150 kilograms times A. Now we have two unknowns here. What we're going to do is solve for T. Then we're going to look at our second box and plug T in. So, if we solve for T, we get T equals, so we add 530 newtons to both sides. 530 newtons plus 150 kilos times acceleration. It got kind of messy over there, but this just comes down to here. And then we have positive 530 newtons. So, you should be doing this on your paper. Just make sure you retain that number. I'm going to erase it all, and we're going to look at box number 2. We can't do anything else with this information. So, box number 2 is going to look like this. Its mass is 250 kilos. Okay? And we have the force of the guy pulling, which is given 1750 newtons. So he's pulling the box this way. Yeah, you see how that works? And then we have the weight pushing down on the earth. The normal force of the earth pushing back, or the ground. And then we have the tension from the string attached to the other box. But we also have to take into account friction for this box, which is going to be resisting the movement of the guy pulling. So we have a total of 5 forces here. We got going towards the right, the dude pulling, which is just the force of 1750 newtons. And resisting that pull is tension from the string attached to the other box, plus friction from the box to the ground. We normally don't do friction in these problems, but this is actually more practical because we usually have friction when we're pulling stuff. And then up and down, we have the weight and the normal force. They are both equal to each other. They're equal to the opposites of each other because there's no movement going on. The box isn't flying up or going down into the earth. So, how do we plug all these variables into an equation that can help us? Again, we're going to start with friction. So we have little f, again, equal to the coefficient of kinetic friction times normal force. So, coefficient of kinetic friction is the same, because they didn't say there's 2 different coefficients here, they just gave us 1, so we're going to use 1, times the normal force, which is equal to the weight. So, we can solve for the weight. 250 kilograms times 9.8, again, 2 significant figures. That is going to come out to 2,500 newtons. Okay? We work this out. We get 880 newtons. Again, 2 significant figures, the 8 and the 8. 180 newtons. So this is our F for this box. The friction is resisting the movement this way with a force of 880 newtons. Okay? That's, again, it goes back to when we first learned about friction. So, what we can do with this is we're going to assemble, again, our equation. Sum of forces equals ma. So I want to box this stuff off so I don't get confused by it. So, we got 5 forces here. In this case, we're only going to look at the left and right, because that's just the x dimension, the horizontal dimension. So we're going to look at the force of the pull, the tension, and the frictional force. So the force of the pull plus opposite of tension actually here, let me make this a bit easier. That looks kind of complicated. So force is going to the right. We define the right as positive. We're going to subtract, since tension is negative, subtract tension, then we're going to subtract the friction. Okay, and that's going to be equal to the mass of the box times its acceleration. Alright, so just take a moment, look at this equation. We have, again, someone's pulling it this way. Resisting it is the tension and the friction. So we have to subtract these two forces from this force, and then we're going to see if there's any acceleration on the object once we plug in its mass. Okay, so we know F, the big F, we know the little f, we don't know the t. So what we're going to do is we're going to go back to our previous equation and substitute t in. So first thing we do is, I'm going to bring this down here for more room. 1750 newtons minus t minus 880 newtons equals the object's mass, 250 kilograms, and then times acceleration, which will go off the board. So, with this equation here, we can set up what we need. So I'm going to erase this chunk over here. Alright, we're going to plug in tension. So I'm going to move this up here. 1750 newtons minus tension. We solve for tension as 530 newtons, remember refer to your notes, plus 150 kilograms times acceleration. Minus 880 newtons is equal to 250 kilograms times acceleration. So that's a big equation here. Let me make it a bit larger. So yeah, go ahead and write this down, and then I'm going to show you how to go through it. Kilograms times acceleration. Okay. Force of the pull, tension, force of friction, mass, acceleration. All we have left is the little a here. So we have the a and the a. We need to isolate the a to solve our equation. Now, what we can do here is, you may be tempted just to subtract 150 from both sides, so you can get rid of the 150 kilograms times acceleration here. Unfortunately, you can't do that because of this negative sign outside of parentheses, so we have to distribute the negative sign first. So, minus 530 newtons, because it's pretty much a negative 1 here. You know, property of distribution, negative 1 times 530, negative 1 times 150, minus 150 kilograms times acceleration, minus 880 newtons. It's going to equal the same thing. Now, we can add 150 kilograms to both sides. 150 kilos times acceleration. We're going to do that to both sides. So we end up with 1750 newtons minus 530 newtons minus 880 newtons. It's going to equal 400 kilograms times acceleration. Okay? Hopefully you're with me up to this point. We can combine all these terms here. But before we do that, we have to, it doesn't depend on the order, technically. You can do it either way. But first, I'm going to divide both sides by 400 kilograms. So that'll get rid of this 400 kilograms right here. We'll just be left with A on this side. So we divide all of this by 400 kilograms. And A will equal. So we're going to do all this math right here. Go ahead and plug that into your calculator. And once you have this number, all the newtons, you're going to divide that number by 400 kilograms. And once we cancel out the kilograms, we get meters times meters over second squared. And remember, we're looking at 2 sig figs here, because we have 2 sig figs in this number. You may say, Eli, there's only 1 sig fig here. This is technically 400.0. I just didn't feel like writing the 0.0. So that's why there's 2 sig figs. So once you do it all, you should get 0.85 meters per second squared. Your number should round to that. This is the acceleration of both boxes after you calculate friction and the pull and the tension. But we're not done yet. We need to find the tension in the strings. So we're going to go back to our tension equation. T equals 530 newtons plus 150 kilograms times acceleration. Okay, so we plug in acceleration. This just goes boop right into there. So 530 newtons plus 150 kilograms times 0.85 meters per second squared. Sorry about that, my camera cut me off at 17 minutes, but anyways, 0.85 meters per second squared. We end up with kilograms times meters over second squared, which is equal to a newton. So we can add these perfectly, and our answer will have one decimal place. Or sorry, no decimal places, because 530 has no decimal places. And in addition, our sig figs, we only look at the decimal place, not the number of sig figs. So our answer will come out to 660 newtons. And if you got a number that's a bit bigger or a bit smaller, you could probably be, maybe within 670, 650 newtons. I'd say that's an acceptable number. But if you're at like 800 or something, your number is a bit off. Same with acceleration. Between 0.79 and 0.89, I'd say is also an acceptable number. But if you're at like 0.34, you're a bit low there. Go back, check your math. Yeah, I really hope this cleared some stuff up. This is, again, probably the most complex problem you're going to see. I don't know if this is going to be on the test. I would say it's probably safe to bet that they'll give us something similar to this, just 5 forces on one object. But again, once you break it down, it's not super difficult. Just have to keep track of your numbers. As you can see, this is like the third time I've erased the board, and it gets pretty long, lengthy. So just go slow. Make sure you're putting your numbers in correctly, and just always double check your work, because you don't want to round incorrectly or have something that's off. Otherwise, your whole problem will be messed up. Yeah, hope you enjoyed. Let me know if you have any questions.